Great, that's working. Can we flip the slides here? Great, yes, thanks very much for attending, everybody. So my name is Julian Chesterfield, and I'm going to talk today about a project that ONAP is participating in. It's actually part of an EU-funded project called ActiCloud with a number of partners. And in particular, I'm going to talk about the partnership that we have with Kaleo, which is a Cambridge-based startup, one of the founders of which is Professor John Goodacre, who's well known to many ARM folk here, I'm sure. And I'm going to be talking about the co-design that we've been working on, particularly on the Kaleo platform, around multi-tenancy virtualization support on low-power ARM-based server architecture. And this is joint work with members of my team, and you know, some of their names are here, and they're also attending today as well. So in particular, the ActiCloud project, just to give a little context, is focused on combating resource underuse in cloud data centers. And the purpose of the project is to identify efficient workload placement policies in emerging cloud server architecture systems. And there's two particular types of systems that we're focusing on. It's scale-up systems and scale-out, both of which use aggregated data center server resources. And so the two hardware partners in particular that we're working with are Numascale, who build a very large distributed scale-up system that uses a special hardware component that allows you to take discrete commodity servers and essentially build a large distributed NUMA, a single memory addressable system. And Kaleo, that is focusing on the scale-out share-nothing architecture, which will in the future be looking towards something called UniMem, which is the ability to borrow memory from different discrete compute components. The system isn't, the UniMem isn't currently available, so I won't be talking about that today, but I will say a little bit about the Kaleo system architecture. So the ONAP focus in particular is at the software layer. So our background is in virtualization. Some of us were formerly part of the Zen development team here in Cambridge. And the work that we're doing at ONAP is focusing in particular on building a much more efficient multi-tenancy virtualization system that is optimized towards low-power ARM infrastructure, particularly focusing around minimizing virtualization overhead. So we focus a lot, particularly on the I/O layer, the I/O subsystem. And one of the particularly interesting things about this project is actually the interrelationship between the standard system virtualization software technology and the integrated FPGA acceleration components, which allows us to build this sort of hybrid software-defined hardware system. So where we can actually use software control for controlling a lot of components, but we can actually accelerate the access and the data path in the FPGA itself. And as part of this work, we've developed a clustered hypervisor architecture that allows us to scale to much larger orders of magnitude than is common today. There's a number of partners involved in this project as well, included here. So as I mentioned, this kind of shows for the ActiCloud project, the relationship between the different partners working on this project. As I say, there's the two hardware partners who are providing the different types of aggregated server resources at the bottom end. ONAP focusing around the multi-tenancy layer, and then we have various application use case providers as well at the top. So the Kaleo compute node, which I'll talk about mostly in this talk, is a new type of server architecture. It's a custom-built PCB board, and it comprises 4 discrete Exynos ARM-based processors with some centralized I/O resources. So this is key to the architecture, and in particular to the scalability of the overall system. It's a very small compute board, and as part of this, we're able to achieve extremely high levels of density in the server system. It's a low-power board with hardware-accelerated I/O. So the FPGA components here. Is it that one? There we go. The FPGA components here. This is the network FPGA that controls all of the external network I/O. This board has dual 10 gig Ethernet external ports, and then there's a storage FPGA here that controls access to the direct attached flash storage on the board itself. So each compute node has its own I/O resources shared across the 4 discrete ARM CPU sockets. The system, the KMax system is, as I mentioned, it's a very dense system. So each chassis has a number of blades associated with it, up to 12. And each blade can hold 4 compute nodes with some integrated network components here as well. So each blade has an integrated 10 gigabit switch with 40 gig uplink ports to the front of the chassis, which allows it to achieve a very high level of density. Just to give you an idea of that, one 3U chassis can contain 12 blades, which in turn can host 48 compute nodes and therefore 192 discrete servers executing on the system. There are full specs available. If you go to the Kaleo website, you can get access to all this information. It's a very dense, very high throughput system that can support a lot of parallel I/O and a lot of parallel processing. So, what are the challenges with the software system in particular? So each compute node board has these discrete sockets that can host a cache coherent system. And then we have shared I/O resources on the side here that we need to be able to coordinate, to control, and to map I/O to the individual systems that execute. And as part of this, we're building a multi-tenancy system, which gives us the flexibility to deploy and configure resources using standard virtualization techniques to take advantage of dedicated resources, isolated CPU and memory access, and also overcommitting of resources for instances that require it. As part of this framework, we also have a lot of very fine-grained control over the types of execution environment that we provide for every, potentially on a per-core basis. So we can configure different types of scheduling algorithms, for example, to execute across different physical cores. And then tying this together, there's some software control. So this is a Zinc FPGA that has an embedded A9 processor as well that allows us to provide a certain amount of control running in software that we can then configure runtime parameters for I/O channels that are exposed to the Exynos processors. So in the storage case, for example, we have a full software-defined storage stack that executes across each of these A9 processors, of which there are many across the whole system. And we're able to configure and to carve up the physical storage resources and create a fully fault-tolerant, highly available, distributed block storage system across this infrastructure. This is actually something that, it's actually technology that ONAP have had for a number of years. We've always implemented this in software. One of the interesting challenges here has actually been figuring out how to modify that technology and to be able to offload parts of that into the I/O data path. So we actually use a protocol called ATA over Ethernet that allows us to to very efficiently transmit block I/O Ethernet frames and convert those inline in the data path actually, and map through the programmable logic directly onto the physical storage drives, which is what we define as software-defined hardware. So, this slide just to illustrate that, what we're dealing with here is something that I would consider to be an emerging theme. So we're not the only people who are sort of looking in this space. It's actually quite a common sort of emerging architecture that we're seeing, where, and we heard a presentation from Noah at Cambridge University in an earlier session today, talking about the CAN-D system, which is a similar sort of concept. The idea that we have centralized I/O resources that are managed via sort of hardware interfaces that allow us to map I/O resources to individual non-cache coherent endpoints, so shared I/O resources across multiple endpoints, with some sort of embedded PCI or fiber fabric. In the KMAX case, this is an embedded PCI bus, but it could equally be some other type of fast interconnect. Systems such as the Facebook Yosemite architecture are a very similar sort of approach, and I think we've heard of other systems today as well that are taking a similar idea. And I would argue that this is a sort of similar problem that we see with, or a similar trend that we're seeing with protocols such as NVMe over Fabric, where we have a very fast fabric interconnect that allows us to distribute physical storage resources, but to be able to access them in hardware at a very fast rate. So some of the challenges around supporting multi-tenancy on ARM systems. We consider it extremely important to have multi-tenancy support. I think it is as important, if not more important, on these low-resource systems, these smaller, low-power devices on ARM as it is on Intel. And in particular, it's crucial to be able to very efficiently utilize the hardware resources. So typically, these systems are much more memory limited. They have less physical core and processing capability available. And we also want to be able to leverage things such as the trusted workload execution framework through the ARM Trust Zone technology, and also looking towards efficient application isolation for systems such as unikernels as well. The ARM CPU architecture is actually very well suited to Zen, and I would draw your attention to the Christopher Dahl paper, which actually gives a very interesting breakdown of some of the performance benefits of the ARM architecture over Intel. However, one of the conclusions of the paper, which is something that we absolutely concur with, is that it's very important on the ARM architecture to be able to minimize the utilization of the system for system management overhead, and in particular to minimize the context switch overhead that is one of the challenges with the virtualization system. So as part of this work, we've been revisiting some I/O architectural assumptions for this system. So a common hypervisor architecture would be that we have this is focusing on the Zen system in particular. We have a type 1 hypervisor layer that sits at the lowest level of the stack. And then we have a control management domain that handles the I/O multiplexing for all the paravirtualized I/O resources, and it is responsible for ensuring that the physical hardware I/O is efficiently presented to the guest virtual machines. So in the ARM case, there's a significant amount of overhead incurred by processing paravirtualized I/O queues from a guest context switching into the host domain, which executes in EL1 kernel space, and then multiplexing the I/O onto the device driver interfaces. So we wanted to revisit some of these assumptions. In particular, we want to minimize the I/O processing, the overhead. We wanted to minimize the resource footprint to make sure we use as little memory and system resource as possible. Also take into account the FPGA I/O offloading capability and be able to bring in the hyper-converged system management resources and to be able to leverage the direct attached storage resources and also the network control that we have through the FPGA interfaces. And also be able to scale to much larger amounts than we do typically today. In the Cleo system example, a single rack of KMax systems can hold up to 2,700 discrete server systems. So we need to make sure that the orchestration framework associated with that is able to manage and control multiple racks of these types of resources. So the approach that we've taken is to create a much more efficient VMM layer that is optimized towards the architecture. So we've essentially moved a lot of the components that are common in the virtualization framework into the type 1 VMM layer, which executes in EL2. And as part of that, we've had to move we've had to create a software packet switch architecture into the VMM layer. So essentially, we're terminating paravirtual IO queues, which terminate in the paravirtualized backend logic that executes within the VMM. And this has the ability to efficiently map the IO resources directly onto the DMA engines of the interface, the device driver interfaces. As part of this, we've also had to move quite a bit of the virtualization control logic. So if you're familiar with the Zen architecture, components such as the Zen bus and Zen store interfaces, which are sort of a standardized interface, we've had to implement quite a bit of that in the VMM layer itself. We actually with significant benefit. So we actually find that the instantiation performance for large numbers of VMs is a lot quicker. I'll show some results in a short while. It's a lot quicker when there's actually no context switch overhead again, and the delay associated with setting up paravirtualized IO queues and so on. And as part of this, we've also implemented a software-defined network layer, which allows us to create encapsulated virtual networks above this physical interface as well. So I think this covers pretty much what I said, just with the exception of, as part of this, we also have to move some of the control interface also into this layer because we need to be able to remotely manage these components. At the FPGA level, we also have logical components that allow us to create virtualized I/O resources and to be able to map those dynamically at runtime to the virtualization layer. So in the KMax case, this sits above a PCI embedded fabric. And as I mentioned before, particularly for storage, we use a very lightweight 80 over Ethernet protocol that allows us to map. In this case here, we've got an integrated block I/O and network handling logical layer that allows us to map virtual block I/O requests directly onto Ethernet frames, which we map through the 80 over Ethernet protocol. And having the software control at this level also allows us to do replication, mirroring, fault tolerance through the programmable logic of the FPGA fabric as well. Sitting above this is the management layer, which is a modified OpenStack infrastructure. So OpenStack itself doesn't scale particularly well to this sort of infrastructure. So one of the key things that we've designed in here is this ability to create essentially clustered pools of resources that we present to the orchestration layer. And we have a lot of levers that we can pull here to determine at what level we aggregate data, both for management, control, and also for collecting statistics and monitoring data. It's designed to be able to scale and aggregate data through across many components distributed across the system. And then, of course, at the user interface level, there's also challenges around how do you manage this sort of scale of infrastructure. So we've been playing with some novel ways of presenting and managing infrastructure. And in particular, for production systems, it's crucial to be able to have visualization and understanding around fault-tolerant zones distributed across a data center. So, for example, you've got clustered resources that are distributed across multiple racks, and we can create pools of resources that are fault tolerance domains, essentially. So we have virtual machine workloads executing in this physical resource, for example, with a failover tolerance domain that allows us to bring up resources across different different physical infrastructure. So I'm running out of time here, so I'll just very quickly show some performance results. First of all, the memory footprint, of course, is significantly reduced. So this is a big win, particularly for the ARM base for the Samsung Exynos processor, which is quite memory limited. Secondly, I mentioned that the orchestration setup time for actually bootstrapping guests is significantly improved as well. Because we've moved all the control components into the EL2 layer directly. So we see that the setup time scales extremely nicely. The performance is significantly improved over a standard Zen system running on the same architecture. The network I/O latency in particular is something that we've focused on. So these results were gathered actually on some XGene boards. So this was before we actually had the latest KMax system. But we did some measurements here around comparing a standard virtual machine running on Zen on the same hardware, comparing against the virtualized I/O path using our modified Zen-like hypervisor, and also comparing that against the comparison point here is a solar flare NIC where we map virtual functions directly through to guest VMs. So we're essentially comparing bare metal PCI access support in a guest against the paravirtualized optimized I/O path that we've measured on our system. And we can see that the difference there is negligible. Same thing here for cross-node, so inter-node measuring performance over the physical network. And we see that the performance measured within a bare metal guest here, the control domain, compares extremely favorably with our virtualized guest performance, as opposed to a standard virtual machine measurement here. And then finally, we also did some measurements of a unikernel framework. So this was measuring the performance of a Redis workload, and we compared, this is normalized results, we compared here against the stock virtual machine, and then running, this is a rump kernel-based unikernel, measuring here on a standard Zen, and then the same unikernel executing on our optimized I/O framework. And the performance is significantly better, about 30 to 50% improvement. So in summary, the ActiveCloud project is something that we're participating in, and in particular, we're investigating efficient use of resources in emerging scale-up and scale-out architecture systems. In this talk, I've focused on the Kaleo KMax hardware, and in particular, the modifications or revisions that we've made to the virtualized I/O architecture in order to reduce the resource utilization and to significantly improve performance. And I've mentioned briefly a little bit about the work that we're doing around aggregation of resources, and in particular, building clustered units of resource that allow us to scale the orchestration framework significantly. So thanks very much, and I'm happy to take questions.
Thank you. Okay, so we've been a bit over, so maybe we have time for one question. Nope. Okay, so in this case, we'll move on to our next speaker.
Okay.
Okay. Where is it? Yeah, what's that number down there? 4. Okay. Bigger. Okay. All right. So thank you very much. So this is a talk about servers, but this is also a talk from a very academic perspective. I've spent about half my career actually in industry, but this is, you'll see why that this is a talk from a perspective of somebody at a university trying to do systems research. And the context here is really the sort of rise of custom hardware, and we've just seen some custom hardware. If you look at the kind of research that's being published in conferences like SOSP, OSDR and stuff, in the field of, for example, rack-scale computing, you'll see some really interesting stuff being done on systems that look a bit like this. Somebody was mentioning Farm this morning, for example. You've got a set of commodity PCs, compute servers, storage servers, some InfiniBand switch, and this is the platform that they're using. Okay? This is described as a fairly typical rack-scale platform for running workloads like key-value stores or analytics, things like that. The problem is it's not typical. If you actually look at what's being sold in industry to do this stuff, there's a lot of custom hardware involved. So, for example, the TwinFin, the Tetza stuff that IBM bought a while ago had a lot of interesting stuff with FPGAs for accelerating some of the data processing close to the storage to reduce the cost of shipping data. If you look inside something like a Spark M7, there's a whole lot of interesting stuff which doesn't take up much chip area in the processor, but is actually pretty specialized. There's some database accelerators here that will actually really accelerate some relational operators. There's a load of stuff like Bloom filters. There's some compression, decompression to reduce cache bandwidth. All this stuff is appearing in hardware that is being used for enterprise computing and used in data centers. And you're seeing other things, TensorFlow TPUs, everyone's heard about that. Microsoft Catapult, anyone here heard of Catapult? So Catapult, yeah, people heard of Catapult. This is the FPGA acceleration for Microsoft Bing. Amazon F1, you can actually rent cloud resources now with FPGAs on them. Baidu have been using FPGAs for a long, long time, for instance. So there's a lot of custom ASICs, a lot of FPGAs in industry. And the reason for this is it's become much easier. It's not exactly easy to build hardware. I'd never claim that. But it's much easier to build custom ASICs in, and the volumes make it justifiable, and the tools make it much easier to do it. And it's fairly easy to rapidly fabricate boards and things like this now. And so you get projects like the Machine, Rapid, F1, that are increasingly building hardware which is dramatically affecting the performance of a bunch of important workloads, okay? So this leaves a problem. If you're at a university, you'll basically have this sort of hardware to play with, but the design space is huge. You can build, in industry, with sufficient market size, you can build hardware to do almost anything. It's really a business decision as to exactly what is it worth building. What sort of workload is it worth catering for and accelerating that's going to actually pay for the development effort. So you're seeing a bunch of specialized product designs, but they're a long, long way from what it is that you can actually have access to at a university if you're buying commodity stuff, and that's what most of us have access to. Now, if you're very lucky, I'm very lucky, and I do feel very lucky to be at ETH, is that we actually do work with companies quite closely, and these companies are very nice to us, and they give us access to custom hardware, which is great. Some of you may also be in that kind of fortunate position. Then you have a different problem. The first problem is to actually get the hardware, okay? So a lot of this hardware, for example, this is a TPU down here. This is being developed by people who run online services, right? Star AAS services, right? These people do not have an interest in selling you a product. They don't have an interest in necessarily even giving you a product, because the support effort for a product which was only really designed to be used internally to the company doesn't make it really worthwhile, okay? So companies are, I think it's highly unlikely that anybody here is going to be able to get their hands on a Google TPU that they'll be able to use to do interesting experiments in their lab, right? The best you're going to be able to get is to be able to run TensorFlow on it in the cloud. If you manage to get the hardware, your next problem is getting the documentation. So here's a Catapult 1 board. We got shipped a load of these. We're very grateful to Microsoft. They arrived in a box. And that was it. No documentation. There was a driver, binary blob driver for Windows. And despite a lot of very helpful emails between us and people like Doug Berger and Derek Chu and stuff have been very helpful, there is a limit to how much you can do if you don't have any documentation for the hardware. And the documentation is, it's expensive to produce, it takes time. Companies don't necessarily have a huge business justification for producing detailed documentation and tutorials for academics to use, okay? Now, suppose you do get the documentation, or you've got, smart people in your lab and postdocs and things like that who can actually figure out how the thing works, then you hit the really big problem, which is most of the decisions about what this hardware looks like have already been taken. Custom hardware is built because there's a definite business justification for it. There's a particular niche which has justified doing that kind of custom hardware to accelerate that kind of class of workloads for that kind of customer, okay? And so if you get access to this as a university, and we've got access to things like, this was the single-chip cloud computer, for example, it's already been designed with a particular use case in mind. And if you're actually planning to do high-impact, long-term research using this platform, you're seriously constrained in what you can do. If you're lucky, you can find ways to creatively abuse it. But for the most part, you're essentially doing research into what the designers of the hardware thought you should do. And while most of us have been in a position, certainly people who work in operating systems have been in a position of staring at a piece of hardware and saying to ourselves, what were they thinking? That's not necessarily a basis for a long-term research agenda, okay? So even when you can get the custom hardware, it's already too late. That custom hardware was designed for a purpose. If you want to do research into what custom hardware should look like, this is not the hardware you should be using. So this is the dilemma. What do we do about this, okay? So we decided to have a look at this, and we had some ideas. And our answer was essentially to build our own hardware, but with a very different set of requirements, okay? And the hardware is called Enzian. What Enzian is it is not designed to be anything that looks like a product, okay? This is not a computer you'd want to buy to actually do something useful in a commercial setting. It's deliberately not that. What this is a computer designed to do systems research, right? It's a massively over-engineered platform compared to sort of products that you would get, okay? So cost reduction, power reduction, form factor, things like that are not a concern in the design of this system. What we want is something that's enormously flexible and is as relatively unconstrained as possible, so that we can actually do some research into what custom hardware might look like in the future and what it perhaps should look like and what the sort of constraints are. Now, the interesting question is, 10 years ago, if you'd asked me the question of, well, could we just build ourselves our own computer? I think the answer would have been no. It's been very difficult for universities for the last 10 or 20 years to build computers. Universities used to build lots of computers, but we haven't done so recently. But I think the same reason that we're seeing custom hardware in industry has meant that we're actually beginning to see the ability for universities to build their own hardware for research purposes. And I think this is very much an exciting time. So we are actually building a computer to do this. I say we. Most of the people who are doing this at the moment are my postdoc David, who's over there in the audience, who's responsible for most of the heroic VHDL hacking that's been involved in this so far, and various other people who've helped with the sort of software side of these things at ETH, including Reto, who's my PhD student, who's also somewhere in the audience here at this point. There he is at the back there. And we've had help from people in industry. And here's the first thing that we built, right? So this is Enzian version 1. So this exists today. What this is essentially two boards plugged together. We have an evaluation board from Cavium. So this is a realistic machine, right? This is a machine that can run big server workloads. It's got a 48-core ARM v8 processor on it. It's got about 80 gigabits a second of network bandwidth coming in, right? So this is a serious, beefy machine. This is not a simulation. This is not a small-scale platform. This is designed to run big workloads. You can run big databases on this. The board we have has 128 gigabytes of DDR4 on it. It's got three DDR4 controllers, so could be higher bandwidth, but not too bad. We have another board, which is from Xilinx, which is a Xilinx evaluation board. This has a big FPGA in it. So this is used to be one of the bigger UltraScale plus FPGAs that you can get, okay? We've got two 100 gigabit Ethernet ports coming in this way. The two are connected using a coherence bus, right? This is Cavium's coherence protocol, but this is the processor interconnect. This is not PCI. We really didn't want PCI. Operating systems people are not keen on PCI. That's a beer conversation. But this gives us 10 gigabytes a second of coherence traffic, okay? Between here. Now, the trick here to get this to work is to implement enough of this cache coherence protocol, which is proprietary, but Cavium have been very helpful in telling us about it, on the FPGA. And this, as many of you have dealt with hardware, won't be surprised by, took a long time, and some fairly heroic work by David. And on Friday, we have the link, as of last Friday, we actually have the link up and running, and we can now start to see flits, and we're now in the world of packets, and we're software people, we like packets, we understand packets, we've got the documentation for that. And so we're pretty excited about this now. We've actually essentially got a coherent FPGA and a serious server class processor up on board. It actually looks like this. This is a picture of David's desk. So here's the Cavium board here. This is the coherence link here. Here's the FPGA board. So this gives us, that's not 80 gigabytes a second. 80 gigabits a second. This is one of 3 links that the processor will support. So, it runs Barrelfish, of course, naturally. You can probably boot Linux on it. We haven't tried, but we suspect there's no real problem. This board by itself will happily run Linux. The next step, which is basically next month, is to actually upgrade this link. So there's actually, the Cavium has up to 24 lanes of CCPI, and that'll give us 30 gigabytes a second of coherence traffic between the 3. And that's basically just 3 of those cables that I just showed on the previous diagram. But the real goal here is to do Enzian v3. And this is the stuff that we're beginning to design right now. And this is the board we actually really want to do our research on. So this has similar sort of arrangement, but we're going to have hopefully a bigger FPGA, some high bandwidth memory, some low latency ultra RAM as well. We'll have a little bit more memory because we can. We'll have the same sort of Ethernet, 2 40 gigabit Ethernets on here. There's a lot of very cool networking hardware on the ThunderX, by the way. It's actually pretty nice. But on the other side here, we're going to basically burn all of the transceivers on the FPGA that we're not using for cache coherence to bring it out. That's going to give us, say, 4 QSFP28 kg. That's 400 gigabits of Ethernet bandwidth, or anything else, right? This is essentially a serial port. You can turn these into PCI Express if you like, NVMe, this kind of thing. Essentially, we've got 6 10 gigabyte a second channels here. And this is a nice machine to do research in. It's relatively unconstrained. It allows us to do all sorts of cool stuff. And I'm going to give you some examples of some of the cool stuff we want to do with it. You can probably think of others. And if you're interested in one of these boards, we should talk. Our goal is that we should not be the only people who are using one of these things. We should be trying to get many people in research to use these things because we think they're useful. Okay? So the first thing is, if you want to do accelerator design, experiment with data accelerators, of course, this is a good way to do it. We've got a big, fast FPGA. We can implement all kinds of cool stuff here. So, you know, if you saw David Wood's talk yesterday, he gave a great talk on sort of border control and things. This would be a really good platform to try that sort of stuff out on here. This is essentially the obvious thing to do, right? We can actually try out all kinds of different accelerator designs. But this is also a really, really cool FPGA support board, right? You've got a serious processor attached to this thing. This is not sort of 4 Cortex-A53s. This is 48 Cavium ThunderX cores, and they're pretty nice, right? They go pretty fast. So we can actually do a lot of, run a lot of software in real time here that actually monitors the FPGA doing things. We're big fans of NetFPGA, and so we've been looking very closely and talking a lot with Noah and with Andrew, who've given us lots of advice and told us lots of mistakes not to make. And so you can imagine this as being quite a good sort of follow-on to NetFPGA. There's a lot of bandwidth coming in here. There's actually quite a bit of bandwidth coming in here as well. You've got a lot of regular conventional compute, but also quite a lot of capacity on the Xilinx and a lot of low latency memory on the Xilinx to be able to do all the cool stuff that people do with NetFPGA, but in more of a sort of compute-oriented platform, but with still, you know, a lot of sort of network bandwidth. So we're pretty excited about doing sort of interesting bits of network protocol here, right? This should be for low latency network protocols, things like that. If you want to look at remote memory, we talked to HP a while back. They have interest in remote memory. If you find yourself strangely dissatisfied with the Gen Z protocol, for instance, you could imagine trying all sorts of interesting experiments here, doing protocol conversion. You can imagine doing things like capability verification, protection on memory. Inside the FPGA, you could sequester one of these processors. You have to think about having this board replicated maybe 50 times in a rack. And then you can sort of sequester each of these using the FPGA, using capabilities to protect remote copies of the local memory, or maybe you just have some disaggregated memory as well. You could experiment by using some of these boards to emulate disaggregated memory. Right? So it's a very flexible, sort of reusable sort of platform. You could even, if you believe cache coherency should and could extend to a very large scale system, I'm not necessarily saying I do, but you know, some people I know do. Some of my best friends believe that cache coherency should extend to the entire rack. You could try it. You can give it a go, right? You can take the coherency protocol here, which is a fairly nice, cleanly designed, fairly straightforward MOSI protocol. And you can actually convert it and run, you know, Gen Z or something else if you want across the fabric on the back here. You've got enough bandwidth here. You could plug this into, you know, a 10 gigabit, or 100 gigabit InfiniBand or Ethernet switch, or you could actually just wire up an interesting sort of folded cloth topology here and go switchless if you wanted to, for instance. Try all sorts of cool stuff. You can also try other interesting things. So we've got a lot of work in my group, not by me, by my colleague Gustavo Alonso, on using FPGAs to accelerate bits of database workloads. Okay, you can really dramatically make a difference to the speed of your database by doing this. And as part of that, they sort of started looking at implementing key value stores in hardware, you know, and things like sort of agreement protocols. So David Zidler, for instance, and Zsolt István in the systems group, they have an implementation of consensus, right? Essentially, it's a version of Raft. It'll do a consensus round in well under a microsecond, right? Among a whole load of machines connected by cables. Now, if you can do a consensus round in well under a microsecond, consensus across a rack is now free, right? Compared with most of the performance of your system. That changes how you think about doing replication in a system. If you can, you know, consensus now becomes essentially free. All sorts of things can be rethought. It's a pretty cool sort of prospect that you can start doing a distributed data store with this kind of sort of performance. So that's another fun thing you could try with this sort of stuff. David gave a talk this morning about runtime verification. Program trace exists on the Cavium ThunderX. You have to do a little bit of a dance to shovel it over the cache coherency protocol into the FPGA, but once you've done that, You can do all the cool stuff he was talking about this morning, and you can do it with 48 cores, and you can offload most of the data reduction and the LTL assertion checking onto the FPGA. You also get to see a lot of cache transactions. You get to see I/O operations. You get to a whole load of power monitoring, all kinds of stuff like that. Suddenly you can start thinking about doing systems research in a very different sort of environment once you've got a platform like this. Other things, you could do fault injection. You can get your FPGA to futz with your server in all kinds of weird and wonderful ways when it's least expecting it. For example, the fact that this is actually on the coherence bus, you can just shoot down cache entries on the, in the ThunderX quite happily. That's what the protocol's there for. You could do cache profiling. You get to see what's happening on the interconnect. You can actually sort of have the FPGA monitoring what's going on in the processor in interesting ways. Could be fun. Here's something I quite like to look at, right? Because part of the theme of my group is, hardware is too complicated, and the hardware design is typically not necessarily done in the way that a system software person would like hardware to be designed. It's typically very hard to use, and there's a few sort of basic schoolboy errors about the interfaces. What you can do, for instance, you can take a description of what an accelerator does, in particular, what sort of inputs and outputs it has, okay? And you can generate, for example, the software on the server side to actually talk to the accelerator, essentially a stub compiler, or effectively something like that. But you can also actually generate the hardware interface itself from the same description. So rather than saying, okay, we're going to design a hardware interface, it's got the following queues, got the following descriptors, things like that, you can actually just say, no, I'm going to describe the semantics of this thing, and I will generate the hardware and I'll generate the software in some provably correct way that'll actually talk to it all at the same go. I think that's kind of exciting. For those of you who like to play with DRAM, for instance, this is a custom DRAM controller that you can actually play around with and do kind of cool stuff, and so on, and so on, and so on. I'm sure you can think of other sort of reasons for using it. It might be fun. It does raise some interesting questions, right? You can use this, you can think of this platform in two different ways. You can think of it as, essentially, I can run different applications on a platform like this. I can treat this as my platform. This is the thing that the application is designed to run on. We can use it for things like network function virtualization, databases, things like that. We've got a bunch of work already on little bits of boards we want to integrate onto this. But you can also think of it as a platform for actually doing the research itself, right? Which is a way to figure out what the right platform would be in the future. Since we have an over-engineered platform, what do you throw out to result in the platform that people would actually want to use in the future? And I think it's important to actually distinguish between these two, because if you're going to claim validity, right, you have to really, in the research community, you have to sort of say, look, are we talking about this as the platform? Which is kind of fun, but it's probably the less interesting case than saying, what is the right platform to use, and how can we explore that design space using this platform? And this really is what makes, I think, Enzian different. This is a platform for us to explore how other people are going to design platforms in the future. That's what makes it different. That's the reason you can't buy it, right, today. And that's the reason we want to build it, because we don't believe that a company with a business interest actually has any real reason to buy this. It's very hard for them to justify it, okay? The higher goal here is really research amplification, right? Is that we've had a lot of interest from other people at other universities who say, can I get one of these? Usually I get three reactions, one of which is, you're completely mad. The second is, but I still want one of these. and the third one is typically sort of, when can I buy it? So we'd like to be able to get this out there in the same way that the NetFPGA people did, or the Planet Lab people did, or the DPDK people did at Intel. We think that this is a good way to sort of change the direction of systems research, make it much, much more relevant to what you can do in industry, but also a lot more fun, right? I think there's a lot of cool stuff you can do here. It breaks out of this model of, I have a processor, I have some memory, I have a network interface, that's what I run my software on. If you look at what's happening in the FPGA community right now, and you see publications in places like VLDB about people moving functionality onto FPGAs, the world is really, really changing. And if you're going to do software research, like I do in academia, you really need something like this in order to stay relevant. There it is. Conclusion is, I think, commodity hardware is unrealistic for running workloads on these days. Vendors can build pretty much anything, as I said. You can build anything in hardware, almost anything in hardware. The question is, what do you want to build in hardware, and what can you justify building in hardware? That's a business decision. It's not our business to tell people what to do. It's our business to give people options. How do we figure out what the options are? We need a platform like this. So thank you very much.
Thank you very much. Is there any question?
How much do you expect it will cost?
How much do I expect it will cost? I have no idea, actually. I recklessly went into this thinking, oh, yeah, what the hell? I think that depends a lot on, so there's various things. I know roughly what the cost of designing and fabricating the first few of these is going to be. That's a cost that I'm absorbing in my research group. We're going to outsource a lot of the board design, but we also have some colleagues in the electrical engineering department who are very experienced with doing these boards, who are acting as sort of, intermediaries between us and the design companies and things. That, I think, is fine. The real question is what the unit cost is. And obviously, the more of these we make, the more that cost comes down. But that cost is really going to be pretty much, what the parts are. And the parts are, much as you would, if you look at the design of this thing, where are we back here? I'll leave this up here because this is probably the most useful diagram. If you look at the design of this thing over here, which we call the west side, is essentially a regular server, right? You can buy these things from Gigabyte, right? You buy a server board from Gigabyte that looks like this, and it's about a little over $2,000. Over this side, this is quite a big FPGA, and actually the cost of this is the big unknown. And actually the cost of this might even affect what choice of FPGA we'll use. The list price of the predecessor to this, which is the one we're currently using, is ridiculously high. Like it's about, 6 times the cost of the evaluation board for it. There's even rumors of people buying evaluation boards and desoldering the FPGA because it's the cheapest way to get it. This is something we're actually talking to Xilinx about. Actually, Xilinx and Cavium have both been enormously helpful as part of this project. We couldn't have done it without their help. But I think this is the big unknown, is how much does this cost? The rest is the one-off cost of design. And then, if we actually do start seeding this to industry, to academics and things like that, then it's going to be, cost of production. This is not a profit-making exercise. So I don't know. If you know how much one of these things costs, let me know.
Okay. We can take another question over there.
Hello. Looks like a very interesting platform, but the real question is, how do we use it? I mean, what do you expose to someone who is interested in this platform? You're giving the IP, you're giving what exactly? I have tried to use a little bit of NetFPGA, and I come across a lot of issues about licensing, things that works, things that you're supposed to buy separately, and things like that. So how do you bundle it with the IP or whatever else is needed so that I can use it directly?
That's a very good question. Andrew Moore here has his head in his hands. That is an issue. And from certainly coming, I'm basically a system software person. This is my first venture into hardware. To a software person, the whole hardware IP ecosystem is completely broken 6 ways to Sunday. It's unbelievable. There's just no composability, reusability. There's nothing corresponding to open source, nothing like that. It's insane. It's extraordinary how this stuff survives at all. Most of the, all the sort of the coherency stuff on here, we've implemented ourselves, right? We would just supply that stuff. We have the IP for that. What we don't have, of course, is this protocol. This protocol belongs to Cavium. It's not publicly available. We have it under NDA from Cavium. Obviously, Cavium are going to be moving away from this with future generations and things. So the question I think that we're trying to figure out with them is, what can we say about this? My preference is that we just ship all of this stuff. Everything we have, we just make completely available. We don't use much third-party IP on here yet that isn't a hardcore. Most of this stuff we've written ourselves. That's something, though, that we have to worry about, and we're talking certainly with Andrew and Noah about the sort of the licensing issues here. I think the culture, though, is changing. I think, trying to read the tea leaves inside inside Xilinx and actually these days in Intel. I think that sort of the IP issues inside here may be changing. I think the Intel acquisition of Auditorium was a serious disruption to that. I hope so. Yeah. I was worried about that from the start. It wasn't enough to stop me deciding to press ahead with it. But yes, I hope it doesn't kill it.
Okay. Thank you very much. In the interest of time, we're going to move on. I would.
Right, good afternoon, everybody. I want to wake you from your post-lunch slumbers, and normally I'd start a talk like this by saying, put your hand up if you own a Raspberry Pi, but hopefully, if you've looked inside your ARM Summit bag, you will have noticed that you do now own a Raspberry Pi. So I guess the question is, put your hand up if, before you registered for the Summit, you did own a Raspberry Pi. Yes, that's everybody in the room. Wow, almost. And some people put up several hands, so maybe you own lots of Raspberry Pis. So the question is, what would you do if you had thousands of Raspberry Pis? What interesting things could you do with them? And that's what we hope to address in the next 20 minutes or so. So this project is about the Federated Raspberry Pi microinfrastructure testbed, which, if you squint enough, turns into fruit, which is the name of our project. Not fruit like that. So you can follow us on fruit_testbed or go to fruit-testbed.org to find out more about us. We are funded by the Engineering Physical Sciences Research Council very generously. This is a collaborative project between partners at the universities of, deep breath, Cambridge, Glasgow, Southampton, John Moores and Loughborough. So the project goal is massive aggregation. In Theresa May speak, this is tens of thousands rather than hundreds of thousands of nodes. But there we go. At the moment, we're looking at tens of thousands of nodes of low-cost, low-power commodity infrastructure, read Raspberry Pis or similar single-board computers. And the idea is that we want to create a distributed testbed platform for some kind of applications, not quite sure what yet. So the high-level message is we want a data center in every home. You know how in the olden days people used to go to laundrettes to wash their clothes, and now they have their own washing machines? Well, could you do the same thing with data centers? Rather than go to Amazon or Apple or Google, you could kind of do it yourself. Yes, hopefully. So from dozens of million node data centers to millions of dozen node data centers in each home, hopefully. Right, so here we go. Yes, the average British household has 7.4 devices that you could cluster into a data center, or maybe 8.3 or maybe 18, depending on which blog you read. But there are lots of devices out there that you could cluster together. We, at these different universities, have been playing with Raspberry Pis probably since 2012 when they came out. If you look at the sales figures for Raspberry Pi devices, it's a phenomenal curve there. So the latest quoted figures are that more than 11 million Raspberry Pis have been sold, a figure which has probably earned Eben Upton his Fellowship of the Royal Academy of Engineering, which was announced just a few weeks ago. So this is, by some count, Britain's best-selling computer. We have thousands of these Raspberry Pis, and we want to plug them together to do something interesting. And if you're not using your Pi, we want to plug your Pi into our network too. So what happened was, when the Pis first came out, lots of people decided to plug them together just using standard Ethernet to turn them into things like Beowulf clusters, and the University of Southampton were the first people, or at least the ones whose press office was first to announce that they'd created a Pi cluster. And the thing that really impressed the world at large was that it was cased in Lego. So this is, I think, a 64-node cluster here. These are original Mark I Raspberry Pis, and they put an MPI layer on top of this and did very slow supercomputing calculations. That's what it looked like. Okay, and at Glasgow, I'm from Glasgow, we built a similar Pi cluster. Our Lego was a bit more colourful than theirs, perhaps, and a bit more coordinated. And we had, again, round about 64 nodes of Mark I Raspberry Pis, and we used Linux containers and built what we called a scale model data center. So we did some kind of virtualization and ran jobs inside the containers and so on. And we were using this to teach people what data center technology might look like from a high level. At the University of Cambridge, my colleague Aiko, who may be somewhere in the audience, stuck Raspberry Pis onto people and dug out boats in the Amazon, that's the Amazon rainforest, not Amazon the data center people, and then used it to do some kind of monitoring of people and vehicle movement in the jungle, and then used this in a delay-tolerant network to gather the data and find out interesting things about what was going on. So again, this is some kind of decentralized Raspberry Pi cluster here. Our colleagues at Liverpool John Moores University built a very slow Hadoop cluster running on an interpretive JVM with 100 Raspberry Pi nodes. So perhaps these Raspberry Pi clusters, these prototypical clusters, aren't really doing anything very useful, but we thought about other use cases and eventually settled on some of these things like environmental sensing, perhaps external weather stations or internal smart building monitoring and so on with Raspberry Pis, aggregating the data and doing some kind of processing on it at the edge of the network. Doing delay-tolerant networking, as Aiko did, where you've got these data mules moving around and collecting data. Or if you can make your Hadoop cluster a little bit better, maybe you can do low-power big data. So we all got together and decided that we were going to build a large test bed using Raspberry Pi nodes. And at the moment, we've got about 1,000 nodes across 4 UK university sites connected over Janet, the UK academic network. And we did start off using Debian Linux. We're now moving on to Alpine Linux, which is a little bit of a more compact distribution. And we have various middleware layers we can put on top to run different applications. We're planning in the next year or so to grow to 10,000 nodes, and all these nodes are distributed across different universities and federated together. And there are various challenges in managing and monitoring and reconfiguring this test bed. Okay. So one of the UK funding agencies issued a call last year for funding for interconnected internet test beds. And various people came up with various wacky ideas. One of them was to stick mirrors on the ceiling and do kind of low-cost optical networking. Another one was to do IP over smell. So I kind of make a scent and then kind of blow it towards you, and you can kind of have internet packets going with this scent. And we said, well, why don't we do something crazy? Why don't we build our kind of Raspberry Pi test bed as a kind of internet test bed environment? And that's what we're doing, and we want your help. So if you have a Raspberry Pi and you're not using it, please consider donating it to us. And you can do this by simply, if you live in the UK, sticking it in a parcel and writing free post Pi cycle on your parcel, then dropping it into a red Royal Mail letterbox, and it will come through to us eventually, and we'll stick it in our test bed. Consider also what you might use this test bed for, possible use cases for this platform. And if you're interested in sharing our test bed as well, you can either host your applications on our test bed. So at the moment we're supporting things like Docker containers and so on, and you can package up your application and run it on our test bed. Or you could replicate our test bed. All our software is open source, and you could build your own test bed in parallel, or you could federate your nodes to join our test bed as well. And the idea is that this infrastructure is going to go viral, hopefully. So probably you're scratching your head at this point and thinking, well, what would you actually do with a Raspberry Pi cluster that would be interesting and sensible? So if you look at the literature, of which there is lots, you'd find that most people are simply building these kind of small-scale clusters to serve educational purposes. So they're saying, well, in our undergraduate class, we can connect together Raspberry Pis to build a small-scale data center and teach people about data center technologies. This isn't only of use in university curricula, but also people like the Edinburgh Parallel Computing Centre and GCHQ are building Raspberry Pi clusters and take them into schools, so school kids can have some kind of experience of networking technologies and stacks. But there are other more interesting use cases as well, I think. So edge computing is one of them, and that's what we've been doing with our systems, kind of collecting sensor data and doing machine learning on the edge. Disposable computing as well. So if you think about it, right, Raspberry Pis are effectively free. Okay, so they kind of give them away on the covers of computer magazines and things like that these days. You know, you used to get a CD on your magazine for your computer. Now you get a computer on your computer magazine cover. So these are free resources. Can we kind of create an effectively disposable cluster? So not the computer, but also all the infrastructure surrounding it to make the cluster is disposable. And then you can deploy these in harsh environments where you're not expecting them to survive. You kind of, fire and forget your cluster. Resource-constrained computing is another possibility. So at the moment, Pi clusters are probably operating at megaflops per watt. If you look at the green 500 supercomputing list, then machines on that are gigaflops per watt. So it's not, too many orders of magnitude out. So resource-constrained computing is certainly a possibility. And if you think not just about kind of megaflops per watt, but about things like megaflops per renewable watt, then effectively, if your Raspberry Pi cluster is powered by a solar panel, then all your flops are free. And that's a kind of interesting way to consider rebalancing the equation. Number 5, if you were here yesterday, then perhaps you attended the Going ARM panel and you thought about ARM in the next generation HPC environments. Well, you could try out your next generation HPC environment or your ARM data center by building one of these Raspberry Pi test beds. And indeed, Mythic Beasts, the Cambridge-based ISP, will let you rent a Raspberry Pi in their data center for £6 a month. So Raspberry Pis are kind of utility computing in a rather resource-constrained way. Okay, but let's go beyond clusters and let's think about federating not just, individual clusters with some kind of cluster node management, but about having multiple clusters or kind of individual Pis in the wild and having, if you like, clusters of clusters in this kind of setting here. Some of these devices will be behind NATs and so on in kind of firewalled domains. Others will be on the public internet. And we want a way of hosting and managing all these Pis as a kind of coherent test bed. That's the software and hardware vision that we have with our Fruit project here. So just quickly, some key challenges in this project. In terms of the hardware, we want to pack our Raspberry Pis very densely. So these are Pi 3 boards here, which have been crammed together, and we're going to think about distributing power over the kind of metal pillars there, and then we can just feed in Ethernet around the back here on either side. So you can have quite dense Raspberry Pi units clustered together. In terms of the software, we want a secure way of doing peer-to-peer configuration and updating of our nodes, and we are using technology like Surf to distribute torrent files, which allow us to download Puppet configuration scripts that we can then run on our nodes to provision them and set them up for the particular software tasks we want them to run. So this infrastructure is currently being created and tested in our testbed at the moment. And then the kind of applications we might want to run on top include things like machine learning at the edge, volunteer computing, and so on. So what we want to do from a high-level perspective is move from kind of big data centers to micro data centers. And you can help us by donating your Raspberry Pis or by building your own Raspberry Pi cluster and federating with our managed cluster system. And we think micro data centers are the way to go in terms of energy efficiency, in terms of data privacy, and in terms of using these devices which are scattered around your person and your home. So if our project, which is just really kicking off at the moment, is successful, then we're going to have a record-breaking Raspberry Pi-sized cluster. We're going to have this distributed test bed of single-board computers. We're going to have some interesting demonstrator apps, and we're hoping to build a flying data center. So imagine your kind of disposable data center on a drone flying around and doing useful things. Okay, a short commercial break at this point. So, at the University of Glasgow, we are running a MOOC on Haskell. If you're interested in learning Haskell, you can start our MOOC. It begins next Monday. Just Google Haskell MOOC, ignore the advert, some people paid, and we're the first kind of non-advertisement on Google if you look for Haskell MOOC. Okay, and the second thing is, if you really do want to give us your Raspberry Pi, so we don't want to steal these from school kids who are going to learn about computing, which was the original motivation for Raspberry Pi, of course, but you know about computing already, so give us your Raspberry Pi and we'll put it to good use. Okay, good. So a very brief demo. Of course, I run the risk that the demo doesn't work, but let's just see if we can get this to work here. Right, okay, so this is the kind of prototypical management interface for our Raspberry Pi federated cluster here. And if I go and have a look, so at the moment, of our 1,000 nodes, 4 nodes are alive. Oh no, in fact, only 3 nodes are alive here. One is based in Southampton, there we go, and there are 2 in Glasgow that are actually doing something. And this is some metadata about the nodes here. And I might be able to go and have a look at a single node to find out more information about it. So this is just a REST API here that I'm looking at. Shall I go and have a look at that node there? Let's see what that says. So I should have an uptime and a heartbeat and so on. This is probably Greenwich Mean Time, never mind. And I can also, if I want to, go and fetch the SD card image that's running on that. Oh no, I can't. I thought I could. I think if I type in OS there, it should fetch the image. Oh dear, it's all gone horribly wrong. But anyway, you should be able to, in theory, fetch the SD card image for the Raspberry Pi, and then you can put that on your own Pi, or you can register your node with another RESTful API call and say, here's my Raspberry Pi, here's the metadata about it, and then we'll serve you an image that you can then use to boot your Pi. So at the moment, this is kind of a manual process. You kind of have to do it interactively, but soon we'll be able to net boot your Pi into our managed cluster. So thanks very much. That's all there is to say about the Fruit project, and I'd welcome your questions. Or your Pis. Thank you.
Thank you very much. Is there any question?
So is your infrastructure homogeneous, or are you taking any Raspberry Pi?
Yes, so thank you. At the moment, we're looking at using Pi 2 and Pi 3 devices, but eventually we're hoping that you could use any Raspberry Pi, and indeed any single board computer that we can build an image for, perhaps using Yocto or something like that. So the idea is that this is going to be a heterogeneous cluster, and in your metadata, when you register your node, you'll kind of specify its capabilities and so on. Yes, thank you.
Any other question?
Is there any plan of increasing the memory size of future Raspberry Pi? Because at the moment, it is, if you want to use a cluster type of application, it is a bit small. So with a bigger memory size, it will be more interesting.
I know. So you're right, the Raspberry Pi is very resource constrained in terms of the CPU processing capability and the memory. Yes, you're right. But we're trying to treat these constraints as a kind of feature of our project. You're right, there are more powerful ARM single board computers that we could use in our system, but we like the fact that Raspberry Pi is kind of high availability. You know, everyone's got a Pi, so that's why we're focusing on this sort of low end of the kind of the market.
Any other question? No? Okay, so in this case, thank you very much. This was a very fun presentation. I think it's the first time I've seen...
Come save me, baby. I'm calling. Come catch me, baby. I'm falling. Come save me, baby. I'm calling.
The work I'm going to present is performed in the context of the UniServer project. It is a Horizon 2020 project focusing on microservers for cloud and edge computing. So both cloud and its spin-off edge computing are here and they are here to stay. So if we focus at edge computing or fog computing, the main idea is to bring the cloud services closest closer to the users, and there are a couple of reasons to do that. First, some applications need low latency, so it's not possible to move the data to the data center and process them there. In other cases, there is a huge amount of data, and you need to do some pre-processing near the place where the data are produced. In any case, the ability to perform edge computing enables a number of exciting new applications. And the idea is to get to be able to have data centers of small scale in its home, in its business, and in its neighborhood. So there are some key characteristics that are necessary for servers used in edge computing environments. So they need to be extremely energy efficient because they are often out there and you cannot power them. They need to have low deployment costs, they need to have small form factors, and they also, since they are out there, they are not in controlled environments often, they need to be error resilient and robust. So the main idea, the main goal, the main target of the UniServer project is to develop the software and hardware ecosystem that would then support and would enable fog computing. It is a full stack approach which is driven by 3 applications from application partners. One of them is targeted advertisement, and actually it is analytics on social networks. The other one is a fintech application which actually does checks and reporting on financial transactions. And the third one, I'm going to stay a bit more there because I'm going to use it in a couple of the examples, it is a distributed denial of service attacks monitoring. Okay, so you have a number of antennas in an area, and those antennas get data and they feed data to the edge node, and the edge node tries to identify whether there is a denial of service attack going on. And of course, you understand that this is a good scenario enabled by edge computing. You could not do that otherwise. So, as I said, in edge computing, and actually it is in the main focus of the UniServer project, we need to have power efficiency. Of course, it's not a new problem. It's a common problem spanning all architectures from large data centers, supercomputing, and of course, the fog infrastructure. Now, the main observation driving the work in the UniServer is that hardware is intrinsically heterogeneous. And by hardware, I mean memories, processors, caches, DRAMs, and so on. And there are many reasons for that. So there is manufacturing variability. No 2 chips are the same. And there is variability even within the same chip, even within the cores of the same chip. There was a talk by Dimitris Gizopoulos earlier this morning highlighting exactly this. It described the analysis which is performed at the level of the hardware to find the capabilities of individual chips, individual cores within the chip. So there are a number of variations. Some of them are static. They have to do with the manufacturing process. Some of them are dynamic. They have to do with the workloads executed on the system. And there are also other factors such as aging, the stability of the power network, and so on. So what do we currently do? We try to disregard this fact. And manufacturers try to disregard this fact. So you have different DRAMs and different CPUs, and they can work at different voltages, different frequencies, different update frequencies. And what we actually do is we get the worst frequency of all parts, and we use that as the nominal frequency. or we get the worst voltage of all parts and we use it as the nominal one. Actually, it is even worse because manufacturers, in order to be on the safe side, they also add some guard bands on top of that. So this is extremely energy inefficient, and the main premise of UniServer is to identify those guard bands, identify those limits, and save them. So being able to operate the hardware at the just right configuration for the specific part and the specific workload. So, of course, this involves a lot of work, and it involves all parts of the system. So this is actually the whole stack of UniServer. We start from the hardware. We are using, the main platform is XGen 2 APM microservers. We are going to move to XGen 3 next month. There is a characterization phase on those systems statically, a priori, and then this characterization phase is also repeated during the life of the product periodically. This characterization reveals the guard bands and the margins. And then there is the system software, and the system software tries to configure the system at the just right configuration, as I said, given the results of the characterization and given the characteristics of the workloads. It also tries to control and minimize the effects of potential faults. Again, going back to the presentation by Dimitris Gizopoulos today, what he said is that the analysis identifies 3 regions below the nominal voltage. So in processors, if you go below the nominal voltage, there is a region where things are safe and you don't get any errors. There is another region where you may get errors, okay? And then below that, you will certainly crash. So the objective is to go as close as possible to the end of the safe region without going into the unsafe region. Okay, but when you go away from nominal voltages, you risk getting some errors. So one of the jobs of system software is to control and minimize the effects of those errors. And then on top of that system software layer, there are applications. They can either be standalone or they can be virtualized, running within VMs, also may be controlled by OpenStack. So once again, the idea is to embrace hardware reliability heterogeneity instead of fighting against this heterogeneity. We know that different parts have different characteristics. We know that different parts within the chip have different characteristics. So part of the system is configured nominally, and we know that it is reliable, and parts of the system are configured in those extended margins that we have identified. So this is true for both cores and RAMs. In RAMs, we play both with the voltage and the refresh rate. So we focus on memory and on CPUs because they account for a large percentage of the power consumed in the system. However, at the same time, not all parts of software are equally critical. So there are parts of software and parts of the data which are critical and should be executed correctly, and other parts for which a potential infrequent error would not be that catastrophic. So what we try to do is to schedule, to make sure that critical code runs on reliable components. Critical data are stored on nominally configured DIMMs, whereas non-critical code can run at extended margins, and non-critical data can go to DIMMs configured at extended margins. So let's focus now on the system software, which is actually the topic of this talk. So we want to be able to run in a resilient way, and we also want the system software itself, the operating system itself, to be resilient when running on potentially unreliable hardware. Why do we focus particularly on system software? For two reasons. Because system software, first of all, any error in system software, any error in the operating system has a high probability to prove catastrophic for the system, to result to a crash. The second reason is because, given that operating system code runs at full privileges, the operating system is a medium for the propagation and the amplification of the results of errors. So we want to make the system software resilient, and we want it at the same time to be as efficient as possible. In UniServer, we are using Linux, and we are using KVM as the virtualization platform whenever we are running VMs on top of the system. This is a decision that we rethink a couple of times a day, but on the other hand, you cannot ignore that Linux is the standard operating system used in such applications and such deployments. We think of the decision to use Linux because Linux was not designed with resilience on top of unreliable hardware in mind. Okay, so its architecture is not really helpful. So what is our methodology? Our methodology is to try to reduce system crashes and to try to reduce system crashes overall and to try to constrain any failures to the relaxed domain. So how do we try to do that in the operating system? We try to reduce the footprint of the code of the operating system executed on unreliable hardware. So the critical code, so the operating system and or parts of it are executed on the reliable domain, and non-critical code may be parts of the operating system, but certainly most applications are executed on the relaxed domain. Once again, keep in mind that we are not purposely going to regions in voltage in configuration where errors will occur. Errors may be a side effect. They will happen very infrequently. However, the system needs to be hardened against those errors. So this is a nice idea. However, the problem is that it breaks the SMP assumptions of the Linux kernel. So on Linux, you assume that every application, every process that needs services from the operating system invokes the operating system, and the operating system executes on the core where the process was executing. So in order to make sure that the system is executed on the reliable domain, we need to reroute the services of the operating system. What we do is that we reroute interrupts, system calls, page faults, and also scheduling. So let's focus on system calls first. So the idea is that you have an application. So we switch to privileged mode, and instead of executing the system call on the unreliably configured core, what we do is that we migrate it to a reliable CPU. The system call is executed there, and then as soon as it is executed, we migrate back to the relaxed CPU, and we switch again to user mode. So this looks simple. However, it involves a lot of coding and a lot of assembly magic at those points. The second thing we migrate is the page fault handler, as I said. Interrupts can be easily migrated because it's just a configuration issue. You can configure the system to route the interrupts to a specific core, most of the interrupts at least. So page faults. Similarly, when an application suffers a page fault, we switch to privileged mode. The page fault handler is invoked. However, it does not perform the actual work. It commits the work to be performed to a reliable CPU. The page fault is handled. Page tables are updated. and we wait for the completion, and then we switch back to user mode. Now, for major page faults, it's not much of an issue because they are high latency anyway. In minor page faults, this migration may result to performance issues. I'm going to discuss that a little bit later on. And finally, on the scheduler part, what normally happens is that each CPU picks the next task to be executed on that CPU and context switches to it. Okay, so what we do is that we separate the decision from the context switch. The decisions are taken centrally on a reliable core, and then they are received by the non-reliable cores, and each of those context switches to the task picked by the reliable core. Scheduling is particularly important because the scheduler touches, to a large extent, the data structures of the kernel. So let's go a bit to the effects in resilience of all this exercise. So what we do is that we relax all but one pair of cores. So two of the cores are configured in nominal conditions, and the rest are configured in saving those guard bands. We run this jammer application, this denial of service detection application, and we pin its threads to the relaxed cores. And we have enabled the mechanisms in our kernel. So what do we see? On the vanilla kernel, the problem we had was that 71% of the errors were catastrophic. So you would get no indication either from the hardware or from the operating system. The hardware would just crash. The system would just crash. Only in 29% of the cases we got reported errors, either by the hardware or by the operating system. So what we have achieved with this method is that in all cases, we get indications that something is going wrong before the system crashes. We may not even get a crash. In many cases, we don't get a crash. In the cases we anyway will get a crash, we have a time window ranging from several seconds to several minutes to react. So, of course, this increased resilience often comes at some overhead. The first thing we measured was the baseline overhead of our mechanisms. So we implemented the mechanisms, we activated them. However, we made sure that they will not be used. And we did that by pinning the applications on the reliable cores. And you can see that the overhead is negligible. We have here the overhead, it starts from 0 to, this is 1%. Okay, and the different bars correspond to, the different colors correspond to different applications. So this is Jammer, and this is Lules. Lules is a computationally intensive application from the Coral benchmark suite. Now, so if the mechanisms are just there and they are not used, they don't incur high overhead. Now, when they are used, the picture is different. So focus on the blue bars, which correspond to Lules, and Lules is actually, and this is the representative behavior. So we have overhead, and the overhead is around 7% in this case. I have added the results for Jammer just to show that funny things may happen. So Jammer appears to run faster in this case. It was a really strange result. It can be explained, however, because it is an I/O-intensive application. It involves around 16 threads, if I recall correctly. And by migrating operating system services to the reliable cores, the threads of the application can find a free and reliable core to run more easily. So, again, we can take this overhead as representative. It's around 7%. It wouldn't sound that bad in the context of increase the resilience, but given that energy efficiency is our goal, we are not happy with it. So in order to reduce this overhead, there are a couple of strategies. We can take advantage of structure, and we can selectively apply our mechanisms to certain parts of the system. So an exercise we did is that we tried to evaluate the criticality of different parts of the code and different data structures of Linux and KVM. So what we did is that we performed several thousands of fault injection experiments to different data structures in the Linux code. And we measured the times those injections result to crashes. So here on the vertical axis, it's the number of failures. On the horizontal axis correspond to different actually parts of the system, different modules of the system. And you can see here the results for two applications, the LDBC benchmark and the financial reporting application. So you can see that the critical parts of the system are relatively few. And so you can also see a bad result is that they are different in the two applications. However, they are different in a predictable way. So for example, this application involves databases, and it uses some local sockets for communication. So the network is significant. It is critical. In this case, the financial reporting application does read files from the file system, so the file system is critical. The kernel is critical in all cases because it runs the scheduler and so on. So the second thing we can take advantage of in order to reduce the overhead is temporal patterns. So currently, our current implementation serves a system call or a page fault and immediately returns control to the unreliable core. However, the system calls or page faults often come in batches. So, for example, here we have the page fault frequency of the Jammer application, and you can see that there are a couple of periods during its execution life where it performs many page faults. It is a common occurrence in applications that have phases, for example. So in these cases, it would make sense to keep the application on the reliable core till it exits that phase and not ping-pong among the reliable and the unreliable core. Now, those techniques take care of errors in the CPU. Again, no guarantees. What we are getting is just more graceful behavior than the vanilla, than the original system. Now, concerning memories, they are typically managed in a homogeneous way, so you have the same voltage and the same refresh rate for all memories. And if you try to go to extended margins, you have to do that for all parts of the physical address space. This is work actually from colleagues in the Queen's University of Belfast. So what they implemented is that they implemented different regions, different memory regions within the kernel, and they used that to define mixed reliability ranges in the address space. They operate some DIMMs at nominal conditions and other DIMMs at extended conditions. They place the operating system, the stack, the global, the static, let's say, segment and the code in the normally in the nominal DIMMs, and the rest of the heap to the unreliable. And they have seen that they can reduce DRAM power usage by 23% by taking advantage of this heterogeneous reliability memory with a performance degradation of just 5%. So to conclude, we have seen in the project that hardware margins can be exploited in order to increase energy efficiency. However, the system software needs to be aware of the fact that it is running on mixed reliability hardware. It needs to be adapted. Some simple ideas do not completely solve the problem. However, they are very effective. And of course, they do not come for free. However, the overhead we currently have, which I expect to be improved, does not outweigh the benefits from the increased energy efficiency. So thank you for your attention.
Thank you very much. Is there any question? Yes?
So if I understand you correctly, you're detecting failures by the program crashing, the system crashing.
Either the program crashing or the system crashing, or detecting an SDC at the output of the program.
Right. So, I mean, how do you know that that's actually happened? I mean, what about sort of silent errors or compromise of data?
Those would result,
or or things that may not manifest themselves for a long period of time. You can't trace back to that kind of thing.
Okay. So,
I mean, what's your ground truth here for what's actually happening in the system?
All right. So, given SDCs at the application level, we check the output of the application. Okay. So, we don't. We just check, the one executing, the one actually running on the unreliable cores. So that partially takes care of SDCs. So the other part of your question was latent errors, actually, right? So yeah, this is an issue. And we have actually done this exercise, and we have seen that most of the errors appear immediately. So if I recall correctly, 98%, they appear immediately. However, there are some that may appear up to 10 minutes later. So this is an issue, yes. Again, no guarantees provided. What we are getting and what we wanted to get is to be able to get some observability and get some more graceful behavior with respect to what we previously had, which was, the system immediately crashing. Another issue we have with the specific platform is that it does not behave gracefully as you reduce the voltage. So there is work in the literature for the Itanium, for example, where they reduce the voltage and they first see detected correctable errors, they then see detected uncorrectable errors, and then they have SDCs and crashes. This is not the case for the XGene. So we see SDCs and we see crashes far before we get any indication from the hardware that something is going wrong. And this is actually due to the fact that the Itanium has extra protection for timing errors. It applies continuous clock path deskewing. Okay, so it's not a total solution to the problem. However, we are at a much better shape than we used to be before applying those mechanisms.
Thank you. So thank you very much for these questions and for this talk. I think it's time for us to wrap up. So I hope you enjoyed this afternoon, and I will see you very, very soon. Thank you, everyone.
I'm falling. Come save me, baby. baby. I'm calling. save me, baby. I'm calling. Come catch me, baby. I'm falling. Come save me, baby. I'm calling. Come save me, baby. I'm calling. Come catch me, baby. I'm falling. Come save me, baby. I'm calling. Come save me, baby.